bit late this week, but still during the weekend I promised to come up with the analysis part of our task. So we shall discuss the derivatives. So we saw it already with the polynomials. So with the polynomials, let me remind you that we simply took the shift of the argument by some small delta x. So the x shouldn't be that small here in the picture. And this corresponded to some shift of the value, which is the difference between the new value and the original value. Right, and if you take the second, so if you take so here is the function, and we take simply the 2 points, and going to any of those, you have got the seconds, so this way, and this should tend to the tangent, right? So this is the slope of derivative. So that's what we want to see, and that's very easy to get into a limit expression, and here you see it. So limit of the difference of the values divided by the difference of the arguments, and if this has got the limit, this will be the limiting slope. And of course, if the function was complex valued, so by the definition of the distance in the complex plane, having a limit is the same as having the limit of the real part and imaginary part separately. So there we are, so absolutely nothing new. And of course we want to compute as soon as possible, at least with the help of Sage, so perhaps we want to see some of the known functions to work with. And I told you already that the only thing we can really compute are the polynomials, maybe a quotient of two polynomials, of fx divided by gx if gx is different from 0. Then we shall discuss today how to define the exponential function for all x bigger than 0 and for all a, any real number. And this is the power function this way and exponential function this way. So it depends what we keep as constant and what we consider as the variable. And for all of those, I have listed here in the text the derivatives, and here it's written where it's introduced and computed, right? But the initial idea of the derivative itself is to be able to interpolate our value y of our function f by something which is linear. So it means constant plus the really linear part. So that's what we call affine in the linear algebra. And we can easily reformulate this as understanding that the function f actually is given as the constant value at the x0 plus something which depends on the change of the argument times some function psi. So except of x equals 0, we can explicitly compute what the psi must be. It must be this, right? But the point is that the derivative of f at x0 exists if and only if this function psi can be continuously completed in the x0. So if it exists as a continuous function, and then the value of psi at x0 is the derivative. This is of great importance because if the psi is continuous and is at x0 different from 0, then it will be different from 0 also on a neighborhood, and therefore we know that having the function f with positive derivative means that the slope of the tangent must be positive, must be going up. And it means by this very formula, this one, it means that the function must be always having bigger values than fx0 on the right hand side and less than fx0 on the left hand side. And that's what we describe by saying that the function is growing in that point, increasing in that point. But here is a very interesting example which is easy but straightforward, and let's focus on this example a little bit So here you have the function definition. So at 0 it's 0, and everywhere else it's defined by this. So it's x plus sine 1 over x. So you imagine sine 1 over x is something extremely wiggly. So 1 over x looks approximately this way. So it's just moving as sine x, but all the time faster and faster. Wow, so what was that? Right, so it's faster and faster and all the time going between 1 and minus 1. So this is the x-axis, this is the y-axis, right? So it would just go from up to down. So I didn't draw it the right way, but nearly the right way. And here in the definition of our function, we just multiply it by x squared, and we know that sine goes to 0 approximately like x. So if I multiply with x squared, so it will be actually very quickly going to 0. So around 0 the function will behave roughly like x. So that's what you see here. Then it just moves a little bit when the second term will be adding some great impact by this changing. And then later on one can also just find, if you ask Sage, it will tell you what the limit is. You can see that the limit of the second term in the function to x going to infinity will be again x. So I mean it will be, yes. So it will be something like x plus multiple of x, yeah, and so if we just draw the picture in large scale, then the result would be something like this. So the function would be looking at something which is of this kind, and it would be a little bit wiggling around the 0. You wouldn't see it more or less, right? But if you are close to 0, it's very nicely seen. And the point is, why the example is here, is that it's chosen in such a way that if you compute the derivative, so f0 is 0, so the derivative would be just the function value divided by x. So you see x over x is 1, and here it would be 5x sine 1 over the x, right? And it's easy to compute that this guy has got the limit 1 because this guy has limit 0. And at the same time, everywhere else the f dash will be of this kind, right? Because you have to differentiate it as we know. Well, we shall see it in a moment how to differentiate the product of functions. So this is the derivative, and so you see that actually this thing, so it's jumping between 1 and minus 1. If x goes to 0, so 1 over x goes fast to infinity. And this guy, so sine is between 1 and minus 1, so x times sine of 1 over x will be smaller and smaller. So going to 0, this will vanish, right? So you will have 1 minus 5 times something which is wiggling very fast between minus 1 and plus 1. And so you see on this neighborhood of 0, the derivative will be jumping from plus to minus faster and faster. So definitely f can't be increasing on any interval of around 0, right? So because the derivative would tell that you are growing and well, increasing, decreasing all the time, right? So this is a very special function, and it shows that if the derivative is not continuous, which is our case, so we have got the value at 0, it exists, it's 1, but around 0 the derivative also exists everywhere, but it's not a continuous function, right? And we shall see in one of the later videos today that it's a unpleasant behavior. Right, so now I will not go into details, but there are the elementary properties, right? And the elementary properties follow what we would expect, right? If you imagine that the derivative is something like comparing the small changes in the values of y and x, so if you add two functions, then these changes add up, whereas the arguments remain the same. So the derivative of a sum must be sum of derivatives. It's proven more explicitly below. Similarly with product of functions, right? So if you see how it works with products, so you simply have the right thing here minus the value at x, and here you can add and subtract the things so that you get the same thing as on the first line, right? It's again the same thing, because here I subtract f shifted value minus g in the original x, and here I add f times f shifted times g. So these two things cancel each other, and so you see that we already saw that if f has got derivative, then it must be continuous in the point, and therefore this goes to fx if delta x goes to 0, and what we get there will be the derivative of g if we divide it by del x, right? And here it's just g stays at the x, and this will get you the derivative. So that's the Leibniz rule. Here it is, right? So this is the Leibniz rule. Very nice. And for composition it's even easier. So if you imagine how it is, so the fraction can be improved by cancelling the change of y, and you will get that it's just what we want, right? So this is how we compute. So we first differentiate the outer function, so the one which goes as second, and then we multiply it with the derivative of the inner one, and that's here, right? So that's the rule for the derivative of the composed function. So you see, this is nothing complicated, and for quotients, that's the thing we are still lacking. It's also easy because we can understand the quotient as f times g to minus 1, right? So g to minus 1 is not g inverse, which I'll come to inverse function in the second video. So here we mean the reciprocal value. So hx is simply this, right? So this is what we compute. So it's actually a product, and so if we learn how to differentiate x to minus 1, so this kind of power function, then we immediately can use the rule for computing derivative of products, and we get exactly what's here, right? So it's f differentiated times g minus f as it was times g differentiated, but minus, not plus, and you have to divide by the square of g, and that comes from computing the derivative of the power function x to minus 1 explicitly from the definition, right? And you see that it's minus x to minus 2. Very easy going. Right, so that's what I wanted to say about the derivatives. So that's the first part, and thanks.